the boundary value problem of planar beams, also some special cases for circular or circular arches, for example, and but with moderately larger curvature. So with a curvature that is not particularly large, so that one can assume at the basis of the theory the constitutive equation of the straight beam. So the constitutive equation for beams without curvature. And this is an approximation that can be made in most cases of interest. So we will today instead focus on the case with strong curvature, and I want to start from the point where we arrived yesterday, because what we will derive yesterday is a special case of the equations that we presented yesterday. So yesterday we presented beams with the three-dimensional problem of beams with strong curvature, and we introduced basically a number of quantities that are reduced quantities. They are the reduced area, the reduced moment of inertia, the reduced static moment. And in terms of these quantities that are account for the curvature of the axis line, so they have expressions that are influenced by the curvature of the axis line. So this reduced quantity are not properties of the cross section only, but depend also on the curvature of the axis line. And in terms of these reduced quantities, which have these basically cumbersome expressions, is basically they are defined as the classical quantities, but with the addition of this factor rho over rho minus x2, which is the we will label J in the following, as we have already done several times. This is the Jacobian of the transformation from the coordinate coordinates to any system of Cartesian coordinates, and this J is equal to, is basically nearly 1 for beams with moderately large curvature or small curvature, because in that case rho goes to is a large number. If the curvature, which is the reciprocal of rho, is 0, it means that near 0, it means that rho is approaching infinity. So for those for beams with a moderately large curvature, this J is approximately equal to 1. But for beams with a strong curvature, this J is not equal to 1. We will see some examples later. And so basically these quantities are the analogues of the quantities for the straight beam, but all the integrals have inside this J that multiplies the differential area of the cross section. So our integral over the cross section with J that multiplies the sigma. So obviously we have some more complicated expression, because in J the coordinate x2 is at the denominator, and so we can define these quantities. In order to remember their meaning, their expression, you can just think that is the classical expression of analogous quantity for the straight beam with a J inside incorporated in the integral. So we yesterday we formulated the constitutive equations of the beam with the spatial space beam with strong curvature, which have these expressions, and the direct equations, the inverse equations, and one can introduce this nr, which is n over n minus m over rho. This reduces the axial force m1 over rho, and those are the equations that we obtain. Next, we have an expression also and generalized Navier formula for the curved beam, which is cumbersome and has j in place of x2. We have x2 divided 1 minus x2 over rho. So this is basically x2 or x1 divided this quantity. And we have seen that in most cases, in simple sections, we can simplify. We are still in the three-dimensional case. We can simplify the previous expressions by reducing to 0, g, 1, 2. And so we have these simplified expressions, which are the starting point of the, and this is the generalized Navier formula that form the starting point of the lecture of today. Indeed, now what we do is just restrict our attention to the planar case. In the planar case, there are only only n and then 1, and there are only theta 1 and epsilon, n and then 1 as a generalized stresses and or stress results and resultants and moments, and as a generalized strains, we have only epsilon and theta that will be equal to theta 1. We won't have theta 2. And so also this Navier formula, generalized Navier formula will have only the term with M1. So let's go to the planar case of the beam with strong curvature. And okay. We will use also slightly different. So as you see, we have dropped the terms with theta 2, and we have named theta 1 as theta. And we have only one, this is j rho factor of all the reduced quantities that we have seen before. We have the only one that survives is this j rho, which is the reduced moment of inertia, which is x2 squared over multiplied by rho divided rho minus xr. So what that means? It means that we are also using a different coordinate system, a different notation. Instead of calling x1 and x2 the coordinates along the normal and the binormal axis of the cross section, we call x2. We rename x2 as xr. And we use the notation B for the x1 axis, for the E1 vector, and so for the unit vector of the binormal. This is just a change of notation. So the inverse constitutive equations are written this way. So we can using this reduced moment, it's reducing axial force. We have nr over EA. This equation is similar to that of the straight beam, but with nr that replaces n. And for theta, we have this coupling term m over E j rho, which is very similar to the classical term, minus nr over rho EA. So this is what we have. The analysis of today made by this morning, carried out by Professor Cazzani, assumed constitutive equations where rho is let go to infinity, so that one doesn't have here has only n, and in this other equation has only this term. While in the theory that we are discussing today, we have this more exact constitutive equations accounting for finite curvature. So, how do we use this equation? The implementation of the equations will be discussed tomorrow in the final lecture with some examples. Today, we just overview what will be the use of these equations, and we will also discuss some numerical applications, initial numerical applications. So now the generalized Navier formula reads sigma tt, which is the normal stress in the cross section, is equal to nr over a instead of n, and then we have m over j rho times x r divided by j. This is the generalized Navier formula for the normal stress. And this is not a linear law. This does not correspond to a linear row, a linear equation, because in this term we have the j at the denominator, and so we have a distribution. This is a kind of hyperbolic. So we have that the maximum and the minimum value of the normal stress are not equal to each other, are different, and we have a concentration of the stress towards the point at which basically the radius of curvature of the introduce of the introduce are slightly varied with respect to that of the central line. So we have a concentration of the larger value of the sigma tt at the introduce in this with this denotation of this figure than at the externus. And so this is what we will observe. Now, obviously, we go back to the classical formula when rho goes to infinity, because j rho tends to the moment of inertia of the straight beam, and nr tends to n, and so we have the classical Navier formula. But when the curvature is not small, we'll have this distribution of normal stress, and we will see that the error that can be done by assuming the Navier equation for the normal stress can be also 50%, 60%, very large, if the radius of curvature is high. So this is for the normal stress and the constitutive equation associated with the normal stresses. So the one related to the axial force and the moment, the bending moment. So what about the distribution of the tangential stresses and the constitutive equation for tangential stresses for shear? So in this regard, we should we make use of a theory that is a generalization of the theory for used in straight beam for computing the shear stresses, and by accounting for the curvature of the axis line. We will use equilibrium equations. So this for these quantities, basically we are not using the equations, because the classical beam theory, the beam theory assumes that there is no warping of the cross section. So it means that the tangential stress should be constant over the cross section. This violates local equilibrium equation. So we will develop an extension of the Jurasky theory for shear stresses that is basically is completely obtained through equilibrium equations. This is not strange, because since as Professor Cazzani noticed in the introductory lecture, since we are assuming a constraint theory for the beam, which constrains the cross section to remain rigid, so some part of the stress cannot be derived by the constitutive equation. Is a reaction of this internal constraint, that forces the cross section to remain rigid. So we have a constitutive part of the tangential stresses and the reactive part. The reactive part is associated with the constraint that does not allow warping of the cross section. So by using this equilibrium theory, we obtain the whole distribution of the tangential stress, the constitutive and the reactive part, and through equilibrium, because the reactive part of the stress, generally speaking, in any constrained theory, the reactive part of the stress cannot be derived by the constitutive equations, but needs to be derived by equilibrium equations. Can be determinate or not determinate, but if it can be determinate, it should be derived by equilibrium equation. So we do the same that we do in the straight beam, but accounting for the curvature of the beam axis. So we cut a portion of the beam that is separated from the rest of the cross section by a chord. So we draw a chord over the cross section, and we obtain a subregion, a portion of the beam that is hatched in this figure, and we separate this portion of the beam from the rest of the beam, and we write the equilibrium equations of this portion. In the case of a curved beam, we have to write two equilibrium equations, while in the straight beam we do similar machinery, but we write only the equilibrium equations in the longitudinal direction of this portion, the analogous portion of a beam cut from the wall body. In this case, we have also to write we have two reactive stresses, which are the tangential stresses, tau RT, and the radial stresses, sigma R or sigma RR. We are using the two indices in the sequel. So we have this distribution of radial stresses and tangential stresses over the face, the upper surface of the portion of beam that has been cut from the wall solid. Now we need to write these equations, and we need the equilibrium equations of this portion, and we have to use these equations with some manipulations to obtain the expression for the radial stress and the tangential stress. So we will start by introducing these quantities n bar and t bar, which are the resultant of the normal stresses, now not sigma tt. We should not confuse sigma tt with sigma rr. Sigma tt are the normal stresses on the cross section. Sigma rr are the stresses directed as the axis r. so in the radial direction. And we name n bar and t bar the resultant of the normal stress and the shear stresses on this portion of sigma bar, this portion of the cross section. So next, we write the equilibrium equations of this portion of the beam. How do we write this equation? We have obviously we using the unit. We will make use of the unit unit vectors associated with this section and this other section, which are not the same because there is a curvature of the beam. So we will have minus n E1 minus t ER acting on this T bar, acting on this base. Then we will have n prime EU E T prime, T bar prime, ER prime on this other base, because both n, t, and the unit vectors change on this other base. And then we have the integral of these distributions of radial and tangential stresses, which are applied on the top surface. So we have to take the integral of sigma RR. Why we have this multiplied by the Jacobian? Why we multiplied sigma RR and TRT or prefer by the Jacobian? Because you know, we have to measure the length of this arch, which is not the length of the does not coincide with the length of the arc length measured along this line is not the same as the arc length measured on the beam axis, because there is an x2, there is a and this chord is taken at a distance xr from the centroid. So this is the scale factor that we need to introduce, and then we need to take integrals. So the formulas are slightly different from those used in the Jurasky theory of the straight beam. And then we have a vector equations here because we are multiplying these quantities by the unit vectors of the directions of the corresponding directions. So we have now to work to manipulate these equations to obtain two scalar equations for sigma RR and sigma NTRT. The first thing that we do is to obtain the values of the axial force, the shear force on the second basis, starting from the values on the first basis. In particular, we obtain the product. We expand to Taylor formula, the product T prime ER prime to a Taylor formula, and bar prime E bar ET prime. And we, by using the Taylor formula, truncated at the first order, we can write this results. So we take the derivatives of this quantity, which is obtained when we take the derivative of this quantity. We have to take the derivative of T bar multiplied by ER plus T bar multiplied the derivative of ER. And so we obtain this expression. And analogously, in analogous way, we carry out the Taylor expansion of this quantity. On the other hand, so in this way, we manipulate those terms appearing in the equilibrium equations of this part of the beam. Next, we have to evaluate this integral. And what we do is that we use the mean value theorem. And so this integral, we put this integral equal to the value of the quantity of the integrand, so the quantity that are integrated in a suitable point of the integration interval. So star indicate the value affected by a star are computed at the suitable point in the interval or the interval s and s plus delta s, and we Also AR is computed at a suitable point, and we obtain this expression. We multiply the value at a selected point of these quantities times the amplitude of the integration interval, which is delta s. So this is an application of the mean value theorem. And by replacing these expressions for the forces on the basis of the second base and this integral of the quantities, distributed quantities, sigma RR and TRT, we go back, we obtain this equation. Now, this equation is obtained by replacing these results into the equilibrium vector equilibrium equation, and also we're taking the limit for delta S going to 0. If we do this, we obtain this equation, this limit equation, and which can be split in two scalar equations along the axis ER and ET. And so we have these two equations that we will use to obtain the expression of sigma RR and tau RT. Indeed, by inverting these two equations, we obtain sigma RR equal to 1 over B times the Jacobian dt over ds plus n over rho, and tau RT is equal to this quantity 1 over b. This one is more customary, more customary for students and researchers in structural mechanics, because this is basically the Jurasky formula for the shear stress, which gives the tau as minus. If we okay, this term is also this term goes to 0, but this still, we are not still at the Jurasky formula. We will be at the Jurasky formula in short, but this will become the Jurasky formula. The other one is a new formula for the sigma RR. Now we have to compute this dt over ds and the n over ds, and we obtain by the equilibrium equations of the wall beam by assuming that T bar is A bar or A T, and so we obtain this expression for dt bar over ds. And then and also we remember that the n bar is for regarding n bar, we use the generalized Navier formula, and so we can now since we have to compute n bar here, for example, in the first formula we have to compute the t over ds and the n bar. The n bar, we use the Navier formula. For the t bar over ds, we use this equation, which is just the equilibrium equation of the beam with this scaling factor. And we finally obtain this expression of the sigma RR. Next, for the tau RT, we have to compute for the tau RT, which is the expression, the formula for the tangential stress. We have to compute dn bar over ds. Dn bar over ds is obtained again through this assumption and using the equilibrium equations of the beam. So the dn bar over ds becomes this expression, and finally the expression, which is the generalized Jurasky formula for the curved beam, is the tau is equal to 1 over b times j s bar over jt, and this term is present in the classical Jurasky theory. This term is present in the special case in which in the beam we have, for example, precompression or an axial load. These two terms are are present in the classical Jurassic formula. This other term is additional and accounts for the curvature, which is also accounted for by the scale, this Jacobian that multiplies this term, this coefficient. So these two formulas, in particular, the formula for the tau RT, which has been derived by, so we have treated the tau as a reactive stresses, and we have determined that the tau to equilibrium equations in order to have a more physical, value of tangential stress distribution of the tangential stresses. And now we can use this exact tau formula for deriving the shear factor of the beam. So correct the shear correction factor. So if we here, I think we should have a key. Yeah. So if we have T over gamma, the S, which is the elementary strain energy of the double of the elementary strain energy of an infinitesimal portion of a beam, computed on the basis of the beam theory, and we equal this quantity to the quantity that is obtained through the use of the exact tau distribution, which is on the right-hand side of this equation. We carry out the integral that we replace this tau RT here. We carry out the integral, and we obtain the tau gamma ds is equal to tau squared over j ds times a constant. This constant can be defined as the shear correction factor, which modify the shear correction factor, so the shear correction factor of the curved beam, which permits to account for to correct the beam theory in such a way that one obtains the same strain energy of the exact three-dimensional theory that corresponds to. Obviously, this is true if the cross section is a thin-walled section, because this TRT that we have derived here is the main value of the tau over the chord. Obviously, this is the local distribution of the tau only if and only if the cross section is a thin-walled section. For a thin-walled section, this can be used as an expression for the shear factor, corrected, modified shear correction factor for the curved beam. So, before going to some applications, with this, obviously, this second part related to the derivation, the sigma RR and the tau RT is not necessary for the beam theory. Is necessary when one wants to go beyond. So the results of the beam theory and wants to compute the local stress distribution. One is not satisfied with the value that the expressions and distributions of the generalized stresses. If one needs to go to the local stable stress, one can use these equations for sigma RR and tau RT, and also one has obtained this correction of the constitutive equation for the shear with this shear correction factor. So what is the boundary value problem? Now, this is the boundary value problem. The equilibrium equations are the same as have been discussed this morning by Professor Cazzani. In the equilibrium equation, the constitutive equation, by also introducing the eigen strains, gamma star, epsilon star, theta star. These are eigen strains that are introduced, for example, for thermal, to account for thermal or hygrometric effects, hygrothermal effects, more generally speaking. So if we add this non-constitutive eigen strains, we can write the combination of the compatibility equations and the constitutive equations this way. So this is the total strain, which is the total shear strain, the total axial strain, the total bending strain, which is equal to a part that is constitutive, the elastic part, and plus additional terms that are these eigen strains associated with hydrothermal effects that one may want to account for. And the boundary conditions are the same as have been discussed by Professor Cazzani. Basically, they are natural force boundary conditions, and they require that the values of the stresses or the displacements are known, are prescribed, that are the two bases of the beam. We can also have a simplified model with which assumes that the shear, the elastic part of the shear stress is zero. From now on, when we have these eigen strains, we convene to denote by gamma, epsilon, and theta without any other symbol, the elastic part of the shear strain, axial strain, and the bending strain, while with the star we will denote these eigen strains, and the summation of the elastic part and the eigen strains will give the total strain. Now, if we assume that the elastic part of the shear strain is zero, then we have the Euler-Bernoulli theory, in which basically by assuming that gamma star is also zero, for the sake of simplicity, so there's no eigen strain in the shear. From this equation, if we assume that the summation is zero, because we assume that no gamma star is applied, we can obtain a phi. If this is zero, we can obtain phi as a combination of the derivative of Vr over ds and Vt over rho. So we obtain exactly this result. And so, if we, in this case, for simplicity, we have restrict. No, there is also gamma star here. But here, if we have a gamma star, we should not be able. Okay, there is a contradiction between formula, but let us assume that the gamma star is zero. Otherwise, we get into troubles, and we can manipulate these equations, because we can derive the analogous of the elastica equation for the curved beam. We can try to derive. So let's assume that gamma star is zero. Otherwise, we can get in troubles, and we have to check if this is correct, because in some equation there is no gamma star, in some other equation there is gamma star. So there is a problem here with gamma star. So it's better if we assume that gamma star is zero. And these are the equations. If we want what we cannot obtain exactly the elastic equation for the curved beam, but we can obtain this equation in which is the analogous of the fact that the second derivative of the transverse displacement is equal to the curvature. So like in the, but with this correction term here. So if we ignore these terms of the eigenstrains, this equation generalizes the one in the straight, the one valid for the straight beam with the which states which doesn't show this term and which implies that m over e j rho, which is the curvature, the bending strain of the beam, is equal to the curvature of the beam mass. Here, we obtain a slightly different result, and which is given by this equation. So I would prefer taking a little break because we have some initial numerical applications to show later based on these results. And so I think that we can meet again at 10 after 4 p.m. at 16 and 10. See you in short.